Today the topic of the class is fundamentals of machine learning and feed-forward artificial neural networks with back propagation learning algorithm. The idea is to put us on the same page. So I'm pretty sure that you had classes on machine learning, hopefully. But starting from tomorrow, we will be focusing on attacks against neural networks. And just again, to be sure that we are on the same page, so I prepared this class with kind of a boot camp preparation for the next theoretical modules. So we start with very simple concepts. Within the area of artificial intelligence, we talk about an abstract agent. Either a physical agent like a robot or a software. And the classical definition also assumes that this agent interacts with an environment. So we have environment. And the agent samples the environment through a perception system of some kind. And so the phenomena that is observed, so let's put it as an observation, is recorded through a set of the measurements of the environments. So we have x1, x2, xn. So what those could be? So those could be different characteristics of the same phenomena. It could be characteristics of phenomena of different, which can be described with different modalities. So in concrete terms, one of axes could be a temperature reading from a sensor. Another axe is a reading from a pressure sensor, or all of these axes could be readings from the reception field of a camera. So in this case, axes would be pixel intensities and colors produced by the reception matrix, the receptive matrix. So let's see. So it really depends. I mean, the semantics that you put on this axis really depends on the use case with which you work. So if you work with whether your environment are recordings, some or financial statements or statements about costs of certain assets, then so this axis would be the characteristics of these assets. If you take computer vision example, so this axis would be intensities of pixels. But in either case, so if we just abstract away from a particular use case, we commonly refer this axis over here as features. And if you recall our yesterday's discussion, so features could be of different character. So they could be more or less complex, so to say, or more or less understandable. With respect to characterization of an object, so they can be they could be of a discrete nature, of continuous nature, etc., etc. But The important point for us is that a particular phenomenon that we observe in the environment, sensed by agent, we will characterize from a set of features. And the very first, and our goal is observing the set of features uh, to create a model, internal model of the part of the environment that we observe. And we start with a very simple learning approach on which I will demonstrate some first definitions. And this approach is commonly referred as memory-based learning. Memory-based learning. So it means that the feature vectors from our perception systems are stored in the memory. So we have memory bank, which store all the features that or sets of features that we observe about particular phenomenon. So X uh, 1 X n so 1. So that was one of our observations. Then we have x1 I x I etc. So and we populate our memory with these measurements. Um, and then I want to make this kind of jump into more mathematical treatment of these sets of measurements. And from now on, we will adopt a geometrical intuition or geometrical interpretation. So essentially, so this set of features um, um, of some dimensionality n, we will talk about it as a vector in some n-dimensional space. So what do I mean here? So let's assume, assume that we have a two-dimensional case. Two-dimensional case. So what does it mean? So we have feature x1, x1, um, for example, temperature, and feature 2, x2. Yeah, pressure. Or, I mean, it can be any other modality, of course. And so in this world, with only two characteristics that we can observe, so we can plot possible instances, possible combinations of these measurements on a 2D plane. So we're along x-axis, so we have values for feature 1, and along y-axis values for feature 2. And then basically all our whatever instance we observe through our perception system, so it becomes a point on this 2D plane. And of course, I mean, as any plane, we can define in a region, so some 0, 0 coordinate, where I mean these features are not measured. And in this case, so a specific sample, so let's denote it as X, but now with a bold X, is a vector in this space, which is defined by its coordinates, x1 and x2. All right. And then our agent either moves around, if it can move, or just lives its life and discovers the environment through measurements. So it populated memory with some instances about this environment. So recording all the feature vectors that it observes. And then, of course, in our case, so we will focus mainly on the classification task, meaning that what we want to create a model that sorts out all these measurements in discrete number of categories. So, and for simplicity, we assume binary classification. So basically, we have two categories to model. Sorry, I was distracted by a chat. I thought maybe it was. Yes, we have two categories somehow defined in this world, and we want to create model out of it. And measurements of one class, so just again for visual intuition, we will denote as circles, and measurements of the other class we will denote as pluses. Okay. So our task is to create a model that for any new sample would tell us whether it belongs to one class or to another class. So this is a problem of classification. So on this figure, so I also want to make clear two basic definitions. So in our settings, we might, so the environment, it has, well, by physical reasons, it has these categories. But the measurements that we do, they couldn't be labeled. So we cannot say by looking at the data which feature vector belongs to each category. But we know that there is a structure, so the environment has some structure in it. And what we can do with these vectors, we can try to find this structure without knowing the names of the categories. In this case, we are talking about unsupervised learning. So no labels are available. So we can analyze the displacement of different feature vectors with respect to each other, relative displacement, and try to understand how they cluster together and deduce categories from this kind of analysis. So the second type of learning, so that we will focus on today, is obviously supervised learning. Or learning with a teacher. So it means that we have an entity that uh, gives us names of the categories for each measurement. So labels are available. So we now need mechanisms and methods to decide where a new measurement that we observe, so by sampling the environment, belong to one of the two categories that we have. Given that we stored in the memory all the previous measurements and we mark them with labels. So class 1, class 2, etc. And the well, rather simple and basic, so school level concept, but still a fundamental one in the scope of machine learning. So we need to be equipped with the distances, with the definition of distances, so that we can decide which of the vectors is, or which of the points in this n-dimensional feature space is closer by some criteria to one or another category. So distances. So again, so we have this, in our case, very simple two-dimensional case, x1, x2, but in general we have n dimensions, and now we have two instances in this space, or two samples. So we have data 1 and data 2. So GI are data points. So, and as I said before, so this data points, so they defined by the coordinates, so this vectors, if we talk about the taking into account the origin of the space. And so the options that we have here are several. So first, we have L1 distance, which is Manhattan distance. So which is defined as sum of modulo x so, xi I for data one. Data one. Second.
Are we following that?
Oh, yeah. Be sure that you mute your mics. Thank you. Minus xi d2 all I for all features.
Sorry, I don't get what you're doing. Can you please explain?
Say again.
Sorry, I don't get what you're doing. Can you please explain?
We are defining a distance between two measurements in our, well, two-dimensional, but here it's n-dimensional space. So each of the axes is the measurement of a particular characteristic of the phenomena that we observe. So the axes are features. And in order to enable building a model, so to understand that any given measurement is closer to one to the previously observed measurements of one or another category, we need to be equipped with a distance measure. And here I'm listing again, so this is the school level information, so possible choices for using distances, for defining distances. So a Manhattan distance, so next is obviously our L2, which is Euclidean distance.
So is it about vectors, or vectors maybe are moving, right?
Moving. Well, no, I mean, in this case, it's a static case, so it's our observation. So so take any, let's say um, uh, we take computer vision example. So and let's put it that we have, um, say, so our matrix is 3 by 3, right? And so all the visual primitives that we can do can be described by pixel intensities of the corresponding three by of the corresponding pixel, and you record these activations or intensities, and this becomes your feature vectors, and they are static. So these are so you have set of images. So normally, I mean, so now we are looking a little bit ahead. So the training assumes that you have a data set with these feature vectors, and you have a data set of test vectors, so that are not observable, not observed before. And you want to decide to which of the categories your new observations belong to. So from this perspective, so the data that you have in the training set, so they are static vectors. So just for simplicity of presentation, so I'm talking about a two-dimensional case where we have only two features, x1 and x2. And our task is to define a measure in um, this space. So how two points, how two vectors are close to each other. And there are several options that we have here, starting from Manhattan distance to Euclidean distance, which is defined as square root of sum of squares, or of the differences between the coordinates. And in general form, we have Minkowski distance, which takes form sum modulo x I d1 minus x I d2 to the power of p, and the whole sum is 1 to the power of 1 over p. So this is a general case for a distance measure. And all these all these distances, so they capture different aspects of the magnitude of the coordinates. So, for example, the higher is p, so the more selective this measure is for individual discrepancies for the discrepancies in the individual coordinates. So, if you have 2 points which are different in a single component, so you observe a high difference in magnitudes. So the higher is the distance measure, the higher order distance measure will regard these two vectors, which otherwise are similar, as different. And the lower degree distance you use, so it smoothes out the differences. So basically, Euclidean distance uh, highlights the average discrepancies in the coordinates. Yes, Daniel, please.
Yes, I think you maybe explained for me so I understand. I feel a bit stupid, but what is the purpose of measuring everything and running it? Is it to learn the machine somehow?
Um, well, we are talking about data creating a data-driven model. So and the model should produce as an output. It should produce a category. So whether an object that we observe through a set of measurements, through a set of characteristics, belongs to category 1 or to category 2. So, and for this, we need to be equipped with a measure how different sets of characteristics of the observed object are more or less similar. And this we do
So,
with the distance, with help of distance.
so, sorry. So you want an output from observation with two distances and a measurement um, what the distance are in between, and you have the formulas that you mentioned.
Mhm.
But you want some kind of output, and the output should go for doing what?
So if you look at this figure over here, so you have a system that observes the environment. So, and these observations are stored as vectors of characteristics. So, and you store them in the memory. And in the memory, you also assign that an object with these values of the characteristics belongs to category class 1. And the object with this set of characteristics, so these are different values in your measured variables, belongs to class 2. So now the task of machine learning is to get a new instantiation, a new measurement from your sensory system and decide whether it belongs to class 1 or to class 2 based on the previous observations. So that is the fundamental definition of machine learning or data-driven modeling.
So it's a big if-else and with database maybe.
Say again?
It's like if-else, and then you run the databases like an array or something.
You can think about it like this, of course, yes. And you find the closest entry that you previously recorded.
Okay.
Okay,
Thank you.
yeah, sure. Yes. So distances is one thing. So or one way of assessing the proximity of the measurements. And in simple words, and this is should be kind of this is an important intuition in machine learning. So distances capture how much one object must change to become another object. So in the case of machine learning, qualitatively, uh, distances says capture um, how much object I must change uh, to become object J. So that's uh, kind of fundamental property of distances. But there is another way to assess to assess 2 points in the vector space, and this is done by similarity measure. Similarity. Similarity. So similarity measure, on contrary, um, focuses on shared structure. So how two patterns are aligned with respect to each other. So focuses on shared structure. So how two patterns are aligned. And again, graphically, so in our 2D case, so again, we have our measurements, so our data point 1, our data point 2, and maybe our data point 3. So it is here we exercise the vector nature. So we have vectors, D1, D2, and D3. So they all have the coordinates, of course. So the particular values of the features, but the similarity focuses on the angle between the vectors. So basically, how two vectors are similar to each other. So alpha 1 versus, for example, alpha 2. And here again, so I will not spend time on writing down the equation. So we can we typically use cosine similarity. And well, actually, uh, I will give a definition of it. So for vectors x and y, so we have so cosine is defined as dot product x dot product y divided by norms of the vectors x and by the product of the norms. So this is a formal definition of cosine similarity. So there is a basically uh, just straightforward geometrical intuition behind it. So cosine of two collinear vectors is 0, and a cosine of perpendicular vectors is 1. So we can talk about so the degrees of similarity from 0 degrees totally aligned vectors, similar data patterns, to totally orthogonal vectors, which are dissimilar. All right. And then what you will, when being equipped with these measures of proximity of the data points that you have, so you can go on uh, and start building your data-driven model. So, and as I mentioned it already several times, the simplest data-driven model is memory-based. So if I go back a couple of slides, so once again, it is defined here. So you keep all the measurements in the memory, and then using one or another distance measure or similarity measure, you take a new um, measurement of an object. So new set of features or new feature vector. So everything what I say is synonymous. And the distance, compute this measure that you have to all the stored entries that you have. And you choose the closest one. And then you check the label for the closest one and say, okay, so this new instance belonged to category, say, class 2. And that's what you will try as the simplest case of building a classifier in lab 1. So that's what I described is called the nearest neighbor classifier. Actually, one of the simplest ones. And at the same time, still useful. So it produces very accurate results to some extent. However, it has one major limitation. And the major limitation, as you can guess, is the size of the memory. So the more samples of different instances of all these categories that you want to classify you have, so the more memory you need. And now we take a break, 5 minutes. And after the break, I make a rather huge jump to more advanced models, which are model-based classification. So before the break, we talked about memory-based classification, and after the break, we will be talking about model-based classification. And
Yeah.
I will introduce you artificial neural networks. Yes.
Excuse me.
Yeah.
Sorry, before the break, just a quick question.
Yes.
We know the what is it called? Just 1 second. Yeah, we know the Euclidean distance to be the average discrepancies.
Mm-hmm.
So what is the definition for the Manhattan distance and the Maconcy distance?
So as I said, so the higher P you have, the measure focuses on more on individual discrepancies. So basically, so say that you have very, very high P. So in this case, if you have two vectors, which are different in a single coordinate, but the difference is substantial. So
Yeah.
in one vector, you have one coordinate say value 1, and in the other vector you have coordinate 100.
Yes.
So this higher degree, higher order distances will say that these two vectors are very distant.
Different. Yeah.
While the lower degrees, so they focus on on the average, and on the average, so they I mean uh, I mean the value wouldn't be that high, so to say. So this um, so the other components will contribute uh, to the proximity, to the definition of proximity, the other coordinates.
Okay. Thank you.
Recap.
Yes. Could you say that a higher P gives room for more output categories?
I'm thinking how to formulate it more correctly. If you have a case where your measurements of the environment experience very high differences in magnitudes in very specific uh, features, the higher order distances will be more sensitive to this case. I understand. I'm not answering directly your question because you see, it's not very trivial because normally, I mean, sometimes I mean, you have to begin reasoning or logic here from the nature. So how these large differences appear. So sometimes they appear because of different calibration in different sensors that you have. And then again, so a normal step then is to harmonize the values so that magnitude in certain feature doesn't become dominating in the decision making. So for this case, you have all this pre-processing stuff, but you may have cases where indeed certain set of features, so they become, I mean, the phenomenon really manifests in rather large differences in magnitudes. And so even after pre-processing. So and then when designing your machine learning algorithm, so and knowing that you want to kind of select cases with few but large discrepancies, then you probably would go for a large degree distance. But in practice, so you well the only distance you use, I mean, you either use Manhattan distance L1 or L2 Euclidean distance. So, but again, so if you know that, so you want to catch this very high deviations, so you probably want to introduce this extra measure, so which is of higher degree. So let's see. Okay, let's continue. Let's continue and let's go deeper to more advanced stuff. But again, so let's do some soft introduction to it. So before the break, as I said, we focused on memory-based learning. So samples, in this case, data samples are kept in the memory. Labels. So each data sample is assigned a label. And then use distance measure to determine category, or which is equivalent to determine the label. Okay. So the main drawback of this approach, while again, so it makes sense, and especially so in some cases is even more preferable because you don't need much of computation, so it's only memory. But again, so you need to keep all of the training data inside the memory, and then as the memory grows, so then obviously the search time becomes the bottleneck. So we now introduce more powerful approach, and the idea is to construct a mathematical model of these categories. So create a mathematical model of classes. And to make this possible, so we need to introduce two components. So we need something which is called a score function. And something which is called loss function. So let's talk now about these two functions and how they are being constructed. So all in all, well, I could have started introducing this topic well, from a different angle, so from different models that has better geometrical interpretation, like for example support vector machines, which is a really intuitive model and very powerful model based on strict mathematical properties, very explainable. But we will talk about this model-based approach in the context of feed-forward error-corrected neural networks. Artificial neural networks. and and we focus on the supervised learning as before. Supervised case, supervised learning case. And so before the break, I introduced this formalization of observing environment through feature vectors. So, and that will be our input. So our input, so let's put it first with the sign, with the vector sign, but later on I will just use x without any sign on top of it. So we have a feature vector which is described through a set of coordinates x1, x, n. So this is a feature vector. So this would be an input to our model. So the main idea is that a category will be modeled as a weighted sum of features. Class. So again, to contrast to what we talked previously, so in the memory-based case, so we had our feature vectors x1, x2, so that's what we and we keep them in the memory, x only through x some m, and we put in correspondence, or we assign labels. So this is features, feature vectors, and these are labels. So we have class 1, class 2. Let's think about only two classes. Then class 1, and maybe this one is also class 1. So we have combination. We have these measurements stored in the in memory. So for the model based, so we have all this. So we take now. So xj. So there, and this xj is again. So we put it. So its coordinates here. So but now let's put it in a column. So in the transposed form. So we have our x1, xn. Okay. And we make a function. So when where we take each coordinate. So, and here is our function. And we take each coordinate, we input to this function by and multiply it by a weight. So weight 1 and weight weight n, sorry. Yes. And this function, what it will output a number, a score for class Ci, like C1 or C2. And later on, we will be also talking about this function f. So right now, it doesn't really matter. I mean, what is happening in here? Maybe to begin with, you can think of it as a summation. So as a simple summation. But there is more to it, of course. So I'm just introducing main principles. So in the context of neural networks, this function is also called activation function. And so again, this term is purely inspired by research in the neuroscience, where neurons being activated as a reaction on certain inputs. Yes, but again, I prefer to introduce feed-forward neural networks without any connection to biological neurons, rather as purely mathematical construct, which it is, basically. So formally, we so the model of a category or a class is then score C1 equals to f of sum of wi xi. So it's a weighted sum of all the features that we have. So what we want, so the goal is to improve the score by correcting errors. So is to improve the score for class CI by correcting errors. Why do we have errors in the first place? Well, I mean, it comes from the definition or the way how we started to construct this model. So now what we did here, we did a transition. So instead of keeping all this access in the memory, so we want to pick all instances of a particular class and to create a single model for this class. And to do that, so we adopt a weighted sum model. So because it's a simple one, it's a linear combination of coordinates. In other words. But we don't know in advance, so what are these weights? So how much each of the coordinates, each of the features contribute to definition of a class. Because, so you see, the measurements that belongs to a different class, so that they also have well, they share the same features. And we don't have any good intuition to make these weights, to choose these weights such that it from the very beginning clearly defines a certain class. So what we do normally, so we choose these weights randomly. And then, of course, I mean, whenever you see, well, any new instance, even that belongs to a different category, so this specific choice of weights is probably really suboptimal. So we need to, and what does it mean? It means that the score for the sample that belongs to the same class will be very low, simply because we didn't choose weights correctly. So, and here we come to the definition of learning. So we want to observe, we want to observe the output of for a given set of weights, and then we want to improve the score. And we want to improve the score by changing the weights in some intelligible manner. So, a question: how can we observe change in score as a reaction to change in weights? Well, in this case, we need to be equipped with the technique that do that for us. And this technique is called derivatives. So derivatives measure exactly this. So if we have a function, again, I will not spend time, substantial time on this, but so if, for example, you have a function f, so f of x is a function. Or let's make this case a little bit more complex from the beginning. So because we need this intuition before. So let f x of x and y is a function of two variables. Okay. For example, again, a made-up function. So f x and y is a product of the variables x and y. So now you want to see the sensitivity of this of the output of this function based on changes in one of the parameters over here. So in this case, we are talking about taking a partial derivative df by the variable of interest. So basically, setting y is constant. So we don't touch y. So we want to see how a function is sensitive to changes in x. And then, so again, very quickly, the main definition is the f of x now by dx. So it is a limit. So f x plus h minus f of x divided by h. What is going on here? So that's very simple. So we have x and we have f of x. And we have, for example, so a function which looks like this. So this is our x, so that we know the current x, and we want to test so how function f of x behaves when you start to change x to the right or to the left. So and in this case, so you take this small step, so x plus h, and you measure the f of x plus h, right? And that was, so let me remove this. So let's call it just f. So not to be mistaken with particular instantiations. So f of x. And so here, so when you do the limit, so you basically converge to very border case where you have this h, so just one step of size h, and you measure this delta so that you can evaluate the function in this x plus h case. And what is going on here is that you can compute tangents of this angle, which is delta and h. So what is going on here is that now this thing over here, so which is a derivative, the geometric interpretation of it, becomes a measure. So how sensitive function is to the change of x. So it will be observed through the values of this tangents, right? So that's so far so good. So now next step, and let me be intensify a little bit here. So we started with a very simple case where we have this x. So our features x n, and we created first activation function, or we introduced first activation function. And then, of course, we in this so for each score. So this is class or C1, and then you have these models for all other classes. C2. So you have set of these models, and you have these weights. So I will not put any indices, so, but they are of course different weights for different classes. So this is our basic model, the base model. And further it was, again, so now I'm kind of making a big jump. Further it was generalized, so this construct was generalized to introduce interactions between weighted functions of the feature vectors. So what we have in feed-forward neural networks artificial neural networks is a kind of nested structure. So where the input is our feature vector x1, xn, and then we have cascade of these functions. Again, the intuition here is that we so basically this structure of underlying phenomena is very complex. So we want to capture non-trivial interactions between feature vectors so that we finally can separate classes into in this model. And for this purpose, we created this nested structure or cascaded structure of functions that at the end produce a score. So score C1, score C C classes. Okay. So this is a kind of a big jump. So far, this model that I depicted here in the box, that has a very strict intuition. So each function here, we create a function that will give us a score. So score is understandable term. So it will give us a number. So how measurements x1 through xn, to which extent they contribute to either class 1 or class I in general. So and the model or the hypothesis is that we can do it by linear combination. So this model will be a linear combination of the coordinates. So that's and the linear combination means that so each coordinate is assigned a weight, which at the end tells how important this specific measurement to the definition of a specific category. So this construct in the box is very easy to interpret. But then again, so this transition to this construct over here is well, it's not really trivial. So I mean, historically it comes by understanding through many years of research, understanding that uh, the approach depicted in the box is way too simplistic. So this linear combination of features not immediately characterize a class. So what is needed? You need that these linear combinations they further interact with each other. So features they interact in some complex way, which define a certain class. And that's why so we have feed-forward artificial neural networks in this form. So we have something which is called layers. So we have input layer and number of hidden layers. Hidden with respect to, I will explain now, hidden layers. Um, and one output layer. one output layer, right? So we have input layer, so that's what we input. Output is what we observe, and the hidden basically means that I mean, there is some magic happening here. So I mean, don't put too much meaning into the definition of hidden layer. But what is important we can now is that what we will do now. So I will write down an analytic form for one specific branch of this complex construct. So what we have here, we have input. So we multiply it with some weight, and we input it into a function, and then we take this result. We again multiply it with weight, a different weight. So let's denote them as stars. And well, let's have only single layer. And then we compute. Oh, sorry, what's happening? Huh. And then we compute the output. The score. So this is also some function f. So so the score then can be written as this composite function, which is f of v prime two primes or two stars multiplied by f multiplied of weights of the first layer multiplied by input. So this is pretty much an analytic form of a single branch like this, from here to here. The important point is that so we still talk about score functions. So it's something that so given an input, so we pass it through a set of functions. So yeah, on each layer we have a linear combination of outputs, and at the end we produce a score. So now, what we need to measure the quality of a score. And obviously we need a new function. So we need a function j, which is called cost function. Sometimes it is also referred as loss function. So which takes the score for class I and the true value. So we are in the supervised. Yeah, Joachim.
Yes, the score, does that come from all the functions from input to function 1 to function 2 or does it come from each function?
Yeah, so the score is this final output.
And how do you determine how many functions it will go through?
Oh, that's a good question. That's a really good question. So that you do by so this is the actually the art of training. So the number of layers, the number of functions, the number of functions on each layer is something which is called hyperparameter. So a hyperparameter means that a parameter that affects the performance. So you always evaluate the outcome of your model based on well-defined metrics. So you, I mean, You can go and find it in the, I mean, in some open sources, but I mean, you can define accuracy of classification, um, um, as well as other measures. So how well your model describes the data you have. And so the selection of number of layers in the cascade and the number of functions you do by testing the quality of the outcomes.
Okay, thank you.
But the training gets so but on each step. So before, so now what your question is about actually the next step. So when you build a model, you computed the accuracy of classification, and then you say, maybe I need what can I do to make it better? And then you start to change the structure of your network. But before that, so you have a training for a selected set of parameters. So for say number for particular number of hidden layers and for particular number of activation functions inside hidden layers. And for this, you need to assess each and every outcome. So for each set of axes on the input and each output of the score, so you want to say how good this score is with respect to information that you have about the sample. Because we are talking about supervised learning. So we have this so something which is called ground truth value. And you do it by function, which is called the cost function. So I will come to this very, very soon. So what you do at the end, you have this score function, and now uh, so this score is included in here. So you want to evaluate. So how you want to change your score, and you change your score by tuning the W's over here, so that the errors are minimized. So the discrepancy between the score and the ground truth. So what you do basically, you compute a derivative of this cost function or loss function with respect to each and every weight in the system. And as you see here, so on this slide, so J is a composite function. So if you want to take a derivative with respect to a particular weight, so you need to take well, derivative of this complex function. So you need to apply a chain rule, which basically says so dj. So you need to take it by d score and multiply it by derivative of the score by specific weight. So that's a very, very simplistic definition of a process, what is happening here. So this derivative over here tells how much changes of weights will result in the change of this function, this specific function j, which is a cost function, and we want to minimize it. Inside the cost function, we have another function, our combination, linear combinations, or actually nonlinear combinations of input, according to this cascaded network. And because of that, you need to apply the chain rule, and then further it can be continued. So it's actually virtually impossible to write a closed form equation that describes the entire network of functions. Okay. So, but what is going on here? So when you do that, that with respect to each weight, so that becomes your gradient. So let me see. So what you do here, you compute gradient. So compute gradient for each weight. So, and your gradient is dj on dw one, and all the weights that you have in your system, dj non dw I, etc., etc. So you compute all this derivative. So the sensitivity of the function of the cost function to the changes in the weights, and basically you're learning then. So what the next step is to adjust the weights. And that's what you do with this following equation, W nu. So for each and every weight, again, so I skip indices here. You do the current, you take the current value, and then you make a negative trend to this particular gradient or derivative with respect to this to this weight. And then normally you have an extra parameter which is called a learning rate. So you don't want to make very sudden jumps back and forth in your optimization process. So you have a learning rate. So at the end, so you do gradient descent. So if you have a function, so you start with weight. Well, let's say we have this 3D case, and so you kind of you want to find optimal optimal value for this weight, and that would be your cost function. So it should be minimized. And you do it by small steps. So you evaluate the derivative in this point, then you take a small step here, and in this case, you kind of eventually you end up in the local minimum for or a global minimum, if possible. Okay, and that is the intuition behind this learning rate, learning rule. So it's important that this learning rate is sufficiently small that you again, so with big steps, you can easily overshoot the needed minimum. So that's why learning rate is normally chosen to be very small value. So now I see the time is over. So tomorrow I will finish well, put some more details on the structure of this neural network. So we will be talking about what are these functions over here, this f's, and what concrete instantiations are normally used for evaluating the losses or errors. So we will be talking about softmax, we will be talking about sigmoids and cross entropy. So do you have any questions for now? Yes, Mohammed.
Yeah, I have a question actually, not about what you're presenting, but how you're presenting it,
Yeah.
as it's very difficult for me to read what you're writing pertaining to the text. So I requested initially also if you're able to write the text with a text tool instead of drawing it as
I
very difficult
I'm not
reiterate.
sure about it, Mohammed, because I don't have a tool to convert it to text. So probably you have to live with it.
Yeah, but when you upload the notes, how are we able to even interpret it?
What do you mean? So I will upload the PDF.
No, I mean when you upload the drawings, as
Yeah.
you did for the last lecture,
Yes.
some of the text is almost very difficult to interpret. So I don't know what's written there.
Yeah.
How will you resolve it?
I don't know.
As
You
you're
have
the
to,
audience.
I guess you have to resolve it for yourself somehow. I mean, this is the first time I hear this kind of comment.